Yeah, hi, I'm Dave Blewett from the Johns Hopkins Applied Physics Lab. I'll be moderating this session on what I think are clearly the most compelling locations for landed science. There's going to be 3 presentations, which I imagine will have a fair amount of overlap, and I think this just reflects the strong emerging consensus on the importance of the opportunities that these locations offer, the magnetic anomalies and swirls. So I think I'm going to give us a bell at 12 minutes and then 2 minutes further to wrap up. And our first speaker is Georgiana Kramer, who should be beaming in from the LPI. There's George. Can you hear us, George?
I can hear you. Can you hear me?
Yep, sounds good, George. Go ahead.
Okay. Hello, everybody. I'm virtually presenting to you why the Mare Ingenii would be the perfect location for priority mission. And let me see, answering the slides. Okay. So, right, as an introduction, I'm telling you where Ingenii is located. It is on the far side of the moon, within the South Polagan Basin. The basin itself has a rim of approximately 325 kilometers in diameter. It has 2 Mare overfilled craters within it, Thomson in the north and Thomson M just below Thomson. And it has swirls. And Mare Ingenii was already selected as a constellation region of interest. So, for those of you who don't know, what is a swirl? It is a high albedo feature with sinuous shape and interweaving dark lanes. Lunar swirls are associated with magnetic anomalies. They impart no topography, and they are optically immature. So let's say that you don't care anything about swirls, even though they're really cool looking, but you are interested in planetary magnetic fields. So here is a planetary body that has no global magnetic fields, but it does have these magnetic anomalies. And shown here in this image, anything that's not a purple or blue is one of these magnetic anomalies. And everywhere we found lunar swirls, which are shown in these boxed regions, those lunar swirls are always associated with a magnetic anomaly. Although, interestingly enough, not every magnetic anomaly has a swirl. For instance, Mare Crisium here has 2 anomalies with no swirls. I've been searching desperately with all kinds of data, but I can't find anything so far. Maybe there's something there eventually. So let's say then instead you're interested in the magnetic fields and you're actually interested in the topology of the magnetic field. Well, some work that was done by Hemingway and Garrett Bethel, as well as others, has shown that the look of the magnetic fields may very well be demonstrating what the look of the swirls might be showing us what the magnetic field's topology looks like. And shown in the top here, let me get my cursor back, okay? This top picture here is the magnetic field lines of a pair of dipoles that are separated by 50 kilometers, oriented horizontally. And then below here in this bottom graph is showing the profiles of these horizontal components of the magnetic field at various altitudes. One at a higher altitude of 20 kilometers and going further and further down. Of course, we're not sure that the look of the swirls is actually showing this because it hasn't been proven, but a mission that would maybe fly very low to a lunar swirl, maybe like on a tethered system, you know, that might be a really good idea. Would actually be able to get low enough to actually see if this is true. If we can actually trust that the way that these swirls look is showing us what the magnetic field looks like. So if you might be interested in space weathering, Mare Ingenii is a great place to go. And by space weathering, in case you're not familiar with this, it is a process that alters the surface of a planetary body that lacks an atmosphere to protect it. These basically come down to micrometeorite bombardment and solar wind implantation, although cosmic rays certainly have an effect, but they're smaller compared to these other 2. And they have some They can have different, they can be affected differently by a magnetic field, for instance. But micrometeorites and solar wind are both responsible for creating nanophase iron and agglutinates and microphase iron and nanophase iron, which have effects on the spectra. So because of the magnetic fields and the fact that they can affect some of the agents of solar wind, of space weathering, there has been work done by myself and several others using a variety of data sets. They have shown that on the lunar swirls, there is some differential weathering going on. The weathering is retarded on the lunar swirls, indicating that the solar wind is probably the dominant form of space weathering, at least at the Earth-Moon distance. This work has shown that weathering by the swirls is effectively turned off, meaning that the magnetic field has deflected the solar wind protons, so that weathering on the swirls is occurring almost exclusively by micrometeorites. While off the swirls, the weathering has been turned up. So the dark lanes and regions adjacent to swirls receive not only their normal flux of solar wind protons, but also might be receiving an increased flux. However, this is the Earth-Moon distance, and if you're interested in space weathering there and elsewhere in the solar system, if these magnetic fields are only affecting solar wind, which is certainly the case, and and this is showing how important, if you will, micrometeorite bombardment is to optical space weathering at the Earth-Moon distance, then it could very well be that the opposite is happening in the asteroid belt, where micrometeorites would be dominating the process. So at Ingenii, which I remind you is located in South Polagan, is a great location to sample fresh material. And not only could you be sampling materials of the same age, meaning that they were petrologically formed at the same time, or exposed by impact gardening at the same time, you could also be sampling them ones that have literally the same age, but different optical maturities. And let's say that maybe you're interested in this phenomenon of surface hydration, what I like to call space dew. In moon mineralogy mapper data, in any optical data, when you look at the lunar swirls, you'll see that on the Mare, they're pretty easily identified because they're bright. And they can be more difficult to distinguish in the highlands. As shown in this image from Moon Mineralogy Mapper, a true color mosaic, you can see the ones on the Mare. You can't really tell that there's much in the highlands. However, the same data set allowed us to see this hydration feature across the lunar surface. And because the magnetic anomaly is the thing controlling the solar wind and where it goes, and the surface hydration phenomenon is associated with solar wind, this Moon Mineralogy Mapper data, we demonstrated that the swirls that appear bright in optical data look dark, with a map of the hydroxyl, relative abundance of hydroxyl, the depth of an absorption feature out near 3 microns. And this is indicating that the swirls are depleted in hydroxyl relative to their surroundings. So let's say that you're interested in heliophysics and solar evolution. So getting pretty far from the moon itself, though. Instruments that are placed at the lunar swirls can be used to measure the efficacy of the magnetic fields in deflecting particles of different mass, and also to measure the charge separation electric field effect, which might be going on there. Moreover, if the magnetic anomalies were formed early in lunar history and have been protecting the surface from solar wind weathering ever since, the swirls may be a great location to sample these ancient solar wind. And let's say that you're interested in plasma physics. Swirls are a place to observe charge-particle interactions with the magnetic field involving some very complex geometries. And in particular, it's a really unique location to study a unique scale of these reactions, because it is larger than a vacuum chamber, but smaller than a global magnetic field. Now let's say that you're interested in some weird energy, weird, I mean, maybe unconventional there, energy resources during a mission. An electric field, which is generated as a consequence of charge separation by the magnetic field, may control space weathering. It may be the ultimate thing that's controlling where the solar wind is going with respect on the lunar surface at swirls. And the restriction of positive ions in a plasma wake can lead to a buildup of negative static electricity on an astronaut's suit or equipment, which could be a danger to astronauts or sensitive instrumentation that can't stand this sort of a charge buildup. So it would be very important to understand these things. And moreover, the strength of such an electric field is actually related to the local gradient in the magnetic field strength, And the geometry of the magnetic anomalies may be controlling the electric field in even useful ways, such as being used for protection or possibly, but unlikely, but possibly some sort of an energy resource. Let's say that you're interested in just getting a nice, safe, flat place to land. The swirls have no topography. They simply drape over any existing topography. So even though they may sort of look like they have a little bit of a bump or a hill themselves, they are actually just flat if it's a flat surface. And this is demonstrated in oblique photography of the swirl areas, and also can be observed in mini RF S-band data, which is showing that the swirl surfaces are disappear compared to the background, and also in diviner rock abundance data. And then, of course, again, a third time reminding you, it is in South Pole Lake, and the probably most desired location to get a good sample from. South Pole Lake is desired because it's a great place to test the cataclysm hypothesis using South Pole Lake impact melt. And especially if you're sending a robotic lander, you would like to get the freshest sample possible. You can go to a swirl and you can sample the freshest material. You can also sample mature material, as I said before, that actually have the same age. And let's say you're interested in basin antipode effects. Ingenii Basin is antipodal to Imbrium Basin, the last major basin. And Ingenii is actually surrounded by this unusual furrowed terrain, which is attributed to the convergence of seismic waves. And some of these blocks may be uplifted portions of the South Pole Lake differentiated melt sheet. So that also makes it an interesting place to sample. And let's say that you're interested in utilizing a skylight. One of the locations where a collapsed pit or skylight has been identified was in Mare Ingenii in Thompson M. Skylights are useful for sustained human presence, as I'm sure that you're all aware, by protecting astronauts from solar storms and prolonged exposure to cosmic rays. And I do not have an end slide, but I am done.
Great. Do we have any questions for Dr. Kramer? Clive.
Dr. Kramer, I got distracted by my day job during your talk. You're going to need mobility, or is a static lander okay? I missed that bit.
Oh, really either will do. Static lander would do with a nice. It really depends on what you're after, whether you need a lander or a rover. But I submit that you only need a lander.
So but a rover would be more enabling, given what you pointed out in this location.
Certainly, a rover would get you more data, would get you more science.
All right, thank you.
Yeah.
Hi.
Yeah, one more. Go ahead.
Yeah, I'm Aditya. Just wanted to know regarding the magnetic cleanliness that might be required if you go to one of these places.
I'm sorry, I didn't quite understand that.
What's the cleanliness requirements in terms of EMI for a lander or a rover that would go there? Because I think the field strengths are pretty low in case you wanted to measure gradients.
Right, so I think the field strengths are pretty low, and people that know better than I say that there are probably not a lot of energy resources in reality. But honestly, I can't answer that. I bet you actually Dave Blewett could answer that better than I.
Yeah, there probably would be some desire to develop a magnetically clean platform, although I think there are techniques that you could do with you sort of your science magnetometer, maybe out on a short boom, and then some other magnetometers that could kind of sense the field from the rover and take it out that way.
Thank you.
All right, let's have one more, quick.
Pete Humphreys, AMS Inc. So, do you believe that a horizontal habitation unit where the double doors would be useful to get your rover in and out with samples, where you could do real experiments, and it's upgradable and reconfigurable with a flat platform sliding in and out? So you've got new iteration, new equipment.
Do I think this would be useful? Absolutely. I think you could pretty much throw anything at Mari and Ingenii and get something absolutely invaluable. It is just obviously the best location to go to. It's just there.
Okay, good. Thanks, Georgiana. Did we clap? I guess we did, yeah. All right. Okay, I'm giving the next talk. So we'll have my slides up here presently. And those are my slides. Is this on? Yep. Is it on? Okay. Good. Yeah. So I'm going to talk about. Let's see. Is this a pointer? Yes. Why magnetic anomalies are so interesting and why they make a really compelling choice for exploration by a rover. Okay. Yeah, there's going to be a bit of overlap between my talk and the previous one. But here we go. Yeah, so lunar magnetic anomalies. You know, the lunar crust contains these magnetized areas, which are, you know, a few hundred tens to a couple hundred kilometers across. We call them magnetic anomalies. They were discovered by the Apollo sub-satellite magnetometers and then mapped globally by Lunar Prospector. And the crustal fields are, you know, they're appreciable. Although, you know, up at orbital altitudes where they're measured by Prospector, maybe 30 kilometers, you know, a few tens of nanoteslas. But continued down to the surface, they could be, you know, a few hundred to, you know, 1,000 or so in these locations. Magnetic anomalies showing up here as green in this presentation. Well, where they come from. Why do we have these sections of magnetized crust on a planetary body that doesn't have internal global magnetic field? Well, there's a bunch of ideas on where they came from. One is that basin ejecta can become magnetized. The idea is that ambient fields can be amplified by compression as this huge amount of plasma that's generated in a basin-forming impact converges on the antipode. Another one of the classic ideas is also has to do with plasma interactions, but this time from the impact of a cometary coma. Again, the field is impressed on the surface, presumably a very shallow magnetization by these plasma interactions from the comet collision. And then perhaps back in the era of the dynamo, if there was one, there was a magmatic intrusion or a slug of impact melt that was magnetized in that field. This is another presentation of the global anomaly map. And you can see that the strongest anomaly on the moon is back here at the Chrysium antipode near Gerasimovich. Strongest on the near side is actually at Descartes. And the most famous, however, probably is over at Reiner Gamma. Now, the presence of these magnetic anomalies modifies the moon's, affects the moon's interaction with the solar wind from what it would be if the moon were just a plain dielectric sphere. And so as the moon goes around in its orbit, it encounters these different plasma environments, and the magnetic anomalies, you know, affect the plasma configuration. And this has been observed by a number of spacecraft from orbit using observing things like the reflected electrons, the solar wind flow, reflected neutrals, and these observations have demonstrated that over the strongest anomalies, at least, there is what the space plasma physicists term a mini magnetosphere. Although again, I'll emphasize that the actual field structure down on the surface in these magnetic anomalies is unknown, and it could be really strong. Okay, now, as we've heard, as it happens, these magnetic anomalies are co-located with these mysterious and beautiful features called lunar swirls. They're sinuous high reflectance markings. They're especially distinctive in the ultraviolet. There are sometimes dark lanes found within the bright portions. There are swirls both in the Maria and in the highlands. The type example is our friend Reiner Gamma here. As Georgiana mentioned, there's no topographic relief. They seem to be just a superficial marking. And also, as she showed, the OH absorptions near 2.8 micrometers in the bright parts of the swirl are weaker than in the surroundings, suggesting that the flux of solar wind protons getting down to the surface in those locations is less than in the surroundings. So where do the swirls come from? There are a number of ideas and different hypotheses linking describing the link between the magnetic anomaly and the swirl. So these include attenuated space weathering. The idea there is that the presence of the magnetic field stands off the solar wind and therefore attenuates the normal soil darkening process, the space weathering, that takes place in other locations. Another idea is that there was a recent impact by a comet or a meteoroid swarm, and that this gas and dust from the comet or these meteoroids scoured the surface in such a way to sweep away the dark, mature regolith and expose fresh stuff. In this case, swirls are very young. There's an idea involving electrostatic dust motions. We heard a bit about this yesterday, that the presence of the magnetic field could influence the hopping of electrostatically levitated grains, and resulting in a sort of accumulation or repulsion of dust from a certain location. And I guess sort of a variant on that has to do with these dust motions modifying the normal highly porous structure of the uppermost surface, the so-called fairy castle configuration of the soil, therefore leading to different photometric properties. So I think because of all these reasons, the magnetic anomalies are really superb natural laboratories where we can examine really key questions in several major areas of planetary science. So, and these are, I think, are really compelling problems that bring together sky science. That's the term that Don Wilhelms used in his book To a Rocky Moon, right? Sky science, plasmas, particles and fields with geoscience. And what's really interesting is that the magnetized region provides a control on one of the key variables in space weathering, the solar wind exposure, because micrometeoroids are not influenced by the presence of the magnetic field. So, yeah, just some of these, key problems that we can investigate, that intersect all within a magnetic anomaly. So, geophysics. What's the nature and origin of the magnetized crust? Relating to the ancient dynamo, the lunar heat, the thermal history of the moon. Magmatic intrusions, magnetized basin ejecta, comet impact, what's the depth of the source, all these things. Space plasma physics, the formation of these mini magnetospheres, the details of the standoff process. What are the fluxes by the energy and species that get down to the ground? How does this change throughout the month? and then the geology and surface processes. Space weathering, which takes place throughout the solar system. We really need to understand it on the moon, and here's this, couldn't have designed a better experiment, natural laboratory here to exclude the solar wind. Solar wind implantation, sputtering, the origin of the swirls, the input to the lunar water cycle. You can go to a place that has greater and lesser proton flux reaching the surface. Electrostatic dust motions and accumulation, which takes place on, thought to take place on other airless bodies, including, asteroids and so forth. And then comet impact. Comets must have hit the moon at some point, right? And in addition to all those key science goals, I think we can address some of these strategic knowledge gaps for human exploration, including things like the resource potential, the movement dynamics of this surface-correlated water-related species, the radiation at the surface. Maybe we'll hear a bit more about that in the next talk. Anything going to the surface will help us with geodetic control. If we have a rover, we're going to learn about trafficability, of course, and then this near-surface plasma environment, which is something that we really need to get a handle on for human exploration. So I would advocate going to Reiner Gamma, just a near-side location for ease of communications. There's some interest in picking certain longitudes that give you the maximum time outside the Earth's magnetotail, so that's of interest. And so based on that, Reiner Gamma, which is over at 59 degrees west, is really ideal. We had this question from Clive earlier, but I think measurements at multiple locations are really needed to fully characterize the magnetic field strength and duration, the access of the solar wind to the surface, the regolith and dust properties, the OH, H2O, time variability, and therefore I would argue that we really need a rover to answer those questions. Sort of a nominal mission, I would say you could land in the center of the Reiner Gamma magnetic anomaly and maybe traverse out to the dark lane, maybe 7 or 10 kilometers. And just to remind everyone, we heard a bit about this in the last couple of days, but one of the Soviet rovers drove 37 kilometers. The Mars rovers have driven, tens of kilometers, of course. And just for back of the envelope computation, if you were able to drive a centimeter per second, you could cover 7 kilometers in like 8 days. So potentially you could do a baseline mission in 1 lunar day, although clearly a rover that could survive the night and allow you to make multiple measurements and expand that linear traverse by driving in a spiral or a grid, to get the aerial coverage that we really need to fully map out the magnetic anomaly. So the instruments, there would be a particles and field suite, solar wind spectrometer to get the energy and flux, vector magnetometer. On a mast, we would, of course, have a stereo camera, and we would want a Visnier instrument so that we can determine the mineralogy, nanophase iron abundance from spectral observations, and of course the key water OH2, OH absorptions. Then something on an arm, a microscopic imager to look at the particle size distribution, this dust accumulations or whatever. We want to know what the particle sizes are. And then additional payload enhancements, there are a lot you could imagine depending on, the amount of money you have. Elemental abundance, Mossbauer, maybe a scraper to make shallow trenches, although you can trench with the wheels. Slow-moving dust detector, that was mentioned yesterday. Traverse gravimeter, we heard about that from Kieran. Electric field probe, and we just heard about the laser retroreflectors. I think everything going to the surface probably ought to carry a retroreflector for all those great fundamental physics reasons. So yeah, just to conclude, I think these special environments, they're a natural laboratory for a study of a wide variety of planetary processes. Such a mission could address these key decadal and SCEM questions in major subdisciplines of planetary science: space plasma physics, geophysics, planetary geology. And as well as contributing to the closing of the lunar SKGs for humans. And we're developing a mission concept that we've named Lunar Compass that we hope to propose for the next discovery round. And we're looking for partnerships, so if anybody has rovers or instruments you might be interested, please let me know. I'd be happy to talk with you. So thanks. Thanks for coming. And will the speaker accept questions? Yes, he will. So Tim Glotch.
Yeah, so given kind of the payload that you talk about and the science that you're interested in, I have no doubt that you could really thoroughly characterize the environment at the surface and learn a lot about the magnetic fields. I guess my question is, with this type of payload and mission, do you think you have enough to really start to differentiate between the potential swirl formation mechanisms, getting at the origins of the swirls? I've been thinking about this a little bit, and I'd be interested maybe later in hearing what Carle and George, or anybody's been thinking about space weathering, think about this, but I wonder if you need a sample from a swirl, on the swirl and off the swirl, to really start to look at these things at the nanoscale and figure it out.
Perhaps, but I think clearly we could do a lot with just the in situ investigation of spectral properties, particle size. Yeah, I think you could start to differentiate between the hypotheses for sure. Yeah. Yeah, I think this is one place where you could do an awful lot without the need. There was this discussion yesterday about everybody wants to get a sample back. This is, clearly you can do a lot without returning a sample.
Dave, a number of the things that you see there suggest to me that we may have multiple processes that have produced magnetic anomalies. One piece of information is you don't have swirls at every anomaly, and but there is a concentration antipodal to some of the big basins. So I think that we better not get too wedded to one origin for geologic origin for these anomalies.
Yeah. I think the strength and configuration of the magnetic field may explain why there aren't swirls at every anomaly, and then there's some other ideas too that I won't go into now. But you're right. Yeah, maintain multiple working hypotheses.
Having looked at the swirl field east of Smith Eye, it is very extensive. In fact, I'm not sure that even the LRO has picked up all of how extensive those swirls are in the highlands as well as in the Mare.
Yep. Yeah. Pete Schultz just described that as a belt from the comet impact. Okay, Noah, quickly.
Yeah, and I'll have more that I'll ask the whole panel. But I would encourage you to think about the idea of really being able to trench and get below 5 centimeters and understand what these things are doing at depth. And I think you might, how superficial are these superficial deposits? What does it mean?
Yeah, we're doing a little bit of work by looking at NAC images and small crater excavations. Lauren Joswiak will be reporting on some of that at the 2018 Lunar and Planetary Science Conference. Okay. But yeah, okay, we better hop to it. So Carle's slides can be put up, and go ahead.
I've got to figure out how to work this thing too.
Oh, yeah.
Okay.
So
one is
that's forward.
Okay.
And then this is the pointer.
Okay.
But you just hesitate a second after you press it for the dot to show up.
Okay, thank you. Well, as the last speaker, I'm a little intimidated to have to wrap up this. However, obviously they put one of the best for the last. So I think with George and Dave and I, who you should note, all worked on independently. We didn't realize each of us were doing this. So you'll find a very common theme throughout all of these talks. My co-author is Ian Garrett Bethel, who couldn't be here today. Okay, let's see if okay, I want to give a brief context just to think about, well, why, what should we be doing, how can we do it next? After Sputnik, it only took us essentially 11, 12 years to get to the moon. Think about that. After Sputnik, And we did all these things. First thing, you know, in '59, the Russians flew past the moon, got this image of the backside. And if you look at a modern LRO comparison, you know, they did pretty darn good, you know, in the first shot past the moon. Then, of course, we had landers, automated sample return landers that the Russians did. And, of course, our Apollo landers, you know, not long in terms of our perspectives after even the first satellite went into space. Okay, so what I'd like to do is sort of bridge that into the long-term human presence and sort of identify the Swirls as one of the best places to be thinking about as perhaps a long-term human presence on the moon. Okay, well, why? We know that humans are frail animals, and they get a radiation environment is very negatively, there's negative effects of the environment if you stay in there for a long period of time. And you have to bury yourself deeply. You have to somehow prevent this radiation from accumulating if you want to work on the surface of the moon. And we know now, and by the end of this meeting, you should recognize there are a few places on the moon that might be nice habitats that can give some of this protection naturally. We've talked about the pits. It is a little bit difficult getting into it, but they're wonderful places that will be good shields. And what I want to come back to today, this last talk, is to point to the Swirls as having not necessarily a full protection, but at least some protection that we know almost nothing about. We are very data limited for the Swirls, and that's why it's high on the list of places to go and make measurements. And I'll go through some of these. Okay, this I can do quickly. You know what Swirls are a bit. They're albedo features, and some of the things that can cause albedo features are composition, Mare Highlands. Other things, of course, are freshness. Impacts are typically very fresh and bright. However, I think Swirls are none of the above. And we'll come back to this again, there's very little topography. Well, there's actually no topography associated with the Swirls themselves, but there is this magnetic anomaly, and that's what makes them so special and so unique on the surface of the moon. Okay, I want to look at this small area south of Reiner Gamma in closer detail to give you a sense of what these look like. Notice the 5-kilometer scale mark. This is what it typically looks like at at visible wavelengths. This is an M-cube image. However, the small fresh craters have exposed fresh material that is very pyroxene rich. As it weathers, that gets replaced by glasses and agglutinates, etc. So if you look at the absorption band of pyroxenes at this site, you can essentially remove much of the weathered aspects, and you can look at the character of these Swirls in beautiful detail. And again, remember that 5-kilometer. This is, just try to imagine what forms these shapes, clearly associated with magnetic anomalies, but this is something we do not see in a normal process on other planetary bodies. Okay, let's move on. You've seen this field. I'm going to highlight some of the ones listed in in blue. We know they're all associated with magnetic anomalies. Some are not, Crisium. But let's start looking at the Gerasimovich one, which notice is on the far side, but is it basically in a highland area. You can see some of the small Swirls right there in the middle, but in highland areas, sometimes the Swirls are difficult to see because you've got bright superimposed on bright. But this area we'll come back to because it's a very important area that has excellent data measured to show this mini magnetosphere. And this is what those data are. This was an instrument that was carried on the Chandrayaan mission called SARA, which is kilo-electron-volt atom-reflecting analyzer. It's an instrument that was a joint instrument by Sweden and India. And what they showed by measuring these, making these measurements from orbit, what's shown here, oh, this really does work. Okay, this is outlined in black is the presence of the magnetic anomaly. But what you're seeing here is how the protons, the solar wind protons, are deflected from this very strong magnetic anomaly. And hence, the concept of a mini magnetosphere is clearly shown in this, one of the strongest magnetic anomalies on the surface. Okay, let's go forward. Let's go to Marginis up there in the corner there. This is one of these beautiful arrays that sweeps across Mare and Highlands. You can see the structure there. We have some M-cube data for one of the portions that crosses the Highlands here, which we'll look at in close detail. This is one of the most unusual strips in that we only have a handful of M-cube data obtained at the full spatial and spectral resolution. And it's wonderful. I wish we had the whole moon with this. But shown here is, again, the brightness image. We're going to do a little traverse where that red strip is. And again, remember, you have the solar wind interacting. It's being deflected. What that predicts then is that the OH should be less in the bright areas of the swirl. Wherever the magnetic field is shielding the surface, the OH should develop less. And what's shown on the right there is the portion of the full resolution spectrum that measures the OH. And what I've done here to enhance this is divide all the spectra along that strip by an average spectrum right up at the top that is not in the swirls, a sort of background spectrum. So what you can see is there's background, which is flat, and as you go into the swirl, you have essentially a negative OH feature. It has weaker OH in the swirl compared to the background. This is shown in map form by the OH band depth. So it's very clear that these areas are protected from the solar wind hydrogen, and consequently the OH is not forming. Okay, where are we going next? I think we're going to go to Reiner gamma, and for all of these things, we clearly have a mini magnetosphere. We clearly protect some of the solar wind radiation. And this we just know from this little bit of data that we have from orbit. The surface rover, I completely agree with Dave, is the best suited to investigate the details, all the things we do not know about these swirls. We know it is partially protected, but we don't know how strong. We don't even know how strong the magnetic field is on the surface. We suspect it's high because we can see it from higher altitudes. But to get those kinds of swirls, it clearly must vary across the surface as well. Since we have protection in the bright areas, the sort of opposite of that is in the dark areas, these dark lanes potentially are enriched in the hydrogen if we're focusing some of the hydrogen towards that. We don't know. The surface, and in particular Reiner gamma that we're going to go to, it's an easy place to go to. It's flat. There's no obstacles in your way. And outstanding geology and space physics science are abundant. So here's again where Reiner gamma is. That's the magnetic anomaly on the surface. Here's the magnetic anomaly from orbit superimposed on the main, what we call the head of Reiner gamma. But while I have this image up, well, actually, no, I can go on to the next one. You can see the overall Reiner gamma head, which has the strongest magnetic anomaly, but you can see a tail going up to the north, and it's more coming down to the south. So this is really quite an extensive array with the highest magnetic anomaly itself in the middle. But if all of these are formed in the same process, then whatever is forming it, we're assuming it's linked to the magnetic anomaly, extends in a variety of different directions. This is lunar LRO data taken at high sun. As you know, they have a different geometry. This is low sun, and at low sun you can see some of the surrounding topography. You can see wrinkle ridges, you can see craters, you can see the Marius Hills up to the north there that the tail sort of starts encroaching upon. This is the topography. Nothing there. This is the Diviner rock map. I've put a hint, although you can't even see it here, I guess it's sort of faded, of the Reiner gamma so you can see where it is. But again, the rock population is nothing to worry about. Okay, so here we are, Reiner gamma. Clearly, there's so many things you need to learn about this, especially if you want to, A, learn the science, but B, if you want to examine this as a potential long-term human habitat. You need a rover. And you can rove across the surface in a variety of different ways, depending on how long you last. A MER-type rover would be ideal. With current technology, we don't have to drive as slow as MER did. We can go a lot faster because we can do it almost in real time. Here's, again, a list of possible experiments. Dave went through these very nicely as well. Clearly, the list can go on depending on how many high-quality instruments you can put onto whatever rover is available. And I think once the properties of these sites are known in sufficient detail, some of the constraints of a human habitat might be not eliminated necessarily, we don't know, but at least will be constrained in the less amount. You may not have to have a 2-meter regolith over you. You may have a much more simple habitat. We don't know, but these are excellent places that could be a long-term place for human habitat. We just need data. And of course, at the same time, you're getting this data for long-term human exploration. You'll have major advances over the scientific understanding of the character and origin of the magnetic anomalies and consequences for the lunar regolith evolution. And I think that's my last slide.
Any questions?
We all will. I hope yours is still on mine.
Okay, sure. Yeah, we have just a couple minutes if we want to sort of have a panel. Are you there, George? Can you hear us? Anyway, we'll start off with Shuai Li.
Okay, so this is the same question to three of you. If you about the OH or H2O, about the water. So if you look at the MCube data, do not look at the 2.82 bands, look at the 2.86 or the rest bands, you won't see those hydration features. So we think the 2.82, I mean at Reiner gamma, not Ingenii. Ingenii does show that. Yeah. So I think it's because Reiner gamma is very close to the equator. So the hydration should be extremely low, maybe lower than a detection limit of the MCube data.
Yeah, that's why I showed the Marginis data, because it's not only the standard, it's our best because it's the high resolution. So you can see it in Marginis with no question.
Carle or George or anyone, do you have an explanation of why some magnetic anomalies show no swirls?
Well, yeah. One of the ideas is just the strength of the field and possibly the orientation might be such. Also, there's some hint that the shielding isn't 100% effective. So material's maturing, but just at a much slower rate than in the normal areas. So some of these may have matured out, but in some cases, if fresh material is tossed in, they're sort of refreshed. And you start over with bright material again. So maybe some magnetic anomalies just haven't been refreshed, whereas others have. Carle may have other ideas.
Well, I have a different, this is a science issue that we all keep debating. Is I'm not convinced the high albedo areas are immature, and that's why I showed that image there, that you have these beautiful swirls, even if you remove most of the signature of fresh material. So we will continue to talk about that, but the question is an important one, and we're data limited. Actually, can I say one more thing? Sure. That people, we clearly want a rover to really address this. You need, but almost anything will give you new data that will allow us to progress. So I don't want to eliminate simple either in situ or low altitude flights. You know, there's anything will give us more information in a data limited situation.
Noah.
Okay, I got a lot of questions, and I'm struggling to think of which one I want to ask. So we're going to flip the coin, and it ends up with suggesting for the rover traverses, and I think in all the ones that I've seen here, you sort of stay within at least Reiner Gamma, you go through the swirls, but really also characterizing what the non-swirl stuff looks like and coming in, whether you start there or go out. And I think maybe they all blend together. Everything blends together now. One of the traverses starts way out and comes through, and that's important because you want to absolutely get the control of what quote normal regolith is as well. So I think, David, you had the concentric circles. Starting those off and landing outside of the swirl and coming in, or vice versa, is an important.
Yeah, I think you could
because the dark lanes aren't going to give you normal either. They're just as bizarre. Right?
Yeah, and you could potentially react based on is the field changing, if not, keep going, that sort of thing, based on what the findings are down on the ground. Because as Carle mentioned, the strength and direction of the field must be just so complicated, down on the surface.
And is there a common, or is there a space, is there a measurement you also want to be making from space as well as to characterize what's going on above the surface simultaneous as well?
Well, there's Artemis in lunar orbit, which can give you the sort of the upstream plasma conditions. So that's useful. Although you can also get that from other satellites. Sure. But yeah.
That's a good point, though, because clearly the plasma interaction with this is very key. So you want to measure it on the surface, but you want to know what's coming in too. So having a well thought out sequence, if that's the primary goal for the experiment, the understanding of the plasma interaction. Yeah.
Okay, it's 10 o'clock, so I think that. Okay, we'll take one more.
Okay, one question. So it's a basic one. So do we have a way to date these swirls as to when they got formed?
That's part of the debate.
Yeah, are they ancient, or were they formed a million years ago by a comet impact? So by constraining the nature of the magnetic field and the characteristics of the regolith at those places, we could try to decide whether they're old or young.
Okay. And one more thing from an engineering point of view was there really haven't been rovers that have lasted into the lunar noon. And Reiner Gamma is pretty close to the equator. So as in when we design, we usually choose the easier one, which is choose mid-latitude and survive or try to survive the lunar noon. So is it a necessity, and is there any unique science if the rover has to be active during the noon?
Well, I think, thermal constraints will just depend on the amount of money, what kind of rover you can design. It'll be designed for the conditions, that it's going to go to.
But landing and doing almost anything will give you major information. One thing I wanted to point out, and this was brought up yesterday, is that, and Dave, you pointed out the unusual photometric properties that are known for these surfaces. It may have its own structure. That if you're going to land, you probably want to hop or do something to get away from that landing area, because you're going to destroy the structure of the surface in that landing area.
Yeah, that's a problem with the static lander.
Yeah.
Okay, it's 10 o'clock, so I'll turn it back over to the meeting organizers to let us know what's up next.
Okay. Thanks, Dave. Thanks for a great session. We